So in the last several lessons, we have dealt with all of these identities that we have been using on this board. We've had the addition, subtraction identities, the double angle identities, and the half angle identities. But these were all identities for sine and cosine. Because when you think about it, sine and cosine are really the same function, just shifted with a phase shift along the x-axis like we've discussed in the past. The tangent function is fundamentally different because it's sine divided by cosine, so it has a completely different shape. So the identities for addition, subtraction, half angle, and double angle identities for tangent, they look a lot different. All right, so I'm going to reveal those to you and we're going to learn how to use them in this lesson. Here are the addition and subtraction identities for tangent. If you have tangent of two angles added together, you'd use this expression. The tangent of two angles subtracted from each other, you have this expression here. You have the double angle identity listed here on the board, and we have three different flavors of half angle identity. When you have an angle divided by 2, you have 3 different choices, and as in the past, we have plus or minus, which we have to pick the sign of based on the quadrant of the angle we're taking the tangent of, okay? So my strategy here is, we're going to focus more on using these identities. Now at the end of the lesson, if you stick around to the end, I'll show you where these come from. I'm not going to derive every one of them because it's just not as important as the sine and cosine identities, but we'll derive a few of them. So just so you can see that these identities, they're not black magic. They don't come from thin air. They're very easy to arrive at, but I don't want to front load the lesson on that. I want to learn how to use them. And then at the end of the lesson, if you're interested, I can show you where they come from. It's worth your time. I wouldn't do it if I didn't think it was worth your time, but just save that for the end. Okay, so let's tackle problem number 1. Let's just say that I ask you to simplify an expression, and I say simplify the following expression. And the expression is tangent of 80 degrees minus the tangent of 20 degrees, and then all of that is divided by 1 plus the tangent of 80 degrees times the tangent of 20 degrees. Now these initial problems are mostly just designed to get you in the in the spirit of using these things. So they're very, very cookie cutter, right? So you have tangent of an angle minus tangent of an angle, 1 plus tangent of the same angle, tangent of the second angle. This is going to fall either into one of these, the addition or the subtraction identity. You can see the form of what we have is very similar. It turns out it's going to match this one here, and what I'm going to do is rewrite that over there so you can see exactly how it lines up. So we're going to write this identity underneath here just so that we can make sure we understand. All right, so I'm going to say recall, right, that we have, it's of the form tangent of alpha minus beta is equal to tangent of alpha minus tangent of beta divided by 1 plus tangent alpha tangent beta. And you can see it matches the form of it exactly. So when you have that, then you can just say that this whole thing is equal to the tangent of whatever the first angle is minus whatever the second angle is, 80 minus 20. So it'd be 80 degrees minus 20 degrees, which means it's the tangent of 60 degrees. Now you could leave it there and say this is simplified, but we all know that the tangent is the sine of the angle divided by the cosine of the angle. And because 60 degrees is one of those nice angles on the unit circle, we can, we can finish solving the problem. The unit circle, if you remember, is a circle right here. 60 degrees is somewhere up here. So the sine of 30 degrees is 1/2. The sine of 60 is a square root of 3 over 2. All right, and the cosine of 60 we all know then is 1/2. We learned this in basic trig. This is the division of two fractions, so square root of 3 over 2. Change this to a multiplication, flip and multiply to be 2 over 1, and then the 2's will cancel, and then you have square root of 3 over 1, which is this the square root of 3, and this is the final answer. All right, so this very complicated looking expression with multiple tangents, 1 plus, minus sign, and all that, can be boiled down to a single tangent of an angle that's not even in the original problem, which we then can calculate the value of. Again, it's a very contrived problem just to get you to learn how to use the identities, all right? So let's move on to problem 2, and we'll have another contrived problem. There's nothing wrong with contrived problems. They help us to learn these identities, or to at least know they exist. What if I ask you to simplify the tangent of 7 pi divided by 12 plus the tangent of pi over 4, and all of that is going to be divided by 1 minus tangent of the 7 pi over 12 times the tangent of pi over 4. All right? So the only difference between this and before is that there's actually a sign flip here, plus and minus. And so we go here, we can see that that matches this form over here. So we're going to write this identity down over here. And you might say, why is he writing these identities over and over again? Well, it's because I'm trying to help you remember it. So, well, I don't want you to memorize it because I don't have them memorized. But by writing them down, you at least remember they exist, right? Tangent of alpha plus tangent of beta. And then on the bottom, you have 1 minus tangent of alpha, tangent of beta. And you can see that this matches exactly. First angle, second angle, first angle, second angle, first angle, second angle, first angle, second angle, and there you go. So we can simplify this whole thing as the tangent of 2 angles added together, but the 2 angles in question are 7 pi over 12 plus pi over 4. Now you can do this in a calculator if you want, but I like to do everything manually that we can. So we're going to go off to the side and take a look at what is 7 pi over 12 plus pi over 4. Well, we want a common denominator. So what we're going to do is we're going to say 7 pi over 12 plus 7 pi over 4. We're going to try for a common denominator of 12. So we're going to take the second fraction, multiply by 3 over 3, and that's going to give us over here 7 pi over 12 plus 7 times 3 is 21 pi over 12. 21 pi over 12. All right, you can see I've already made a mistake, and I do that myself. I wrote the original problem down. Pi over 4 is here. There's no 7 here. All right, that's why this 21, I looked at it, I was like, there's no way there's 21 there. All right, but 3 times pi is 3 pi, so you have a 3 pi over 12. So now we can add these guys. The common denominator is 12, and 7 pi plus 3 pi is 10 pi over 12. Now we can divide the top and bottom by 2, which is going to be 5 pi over 6. Right, so now we have this tangent of the angle, which is now 5 pi over 6. So how do we figure out the tangent of 5 pi over 6? Well, I don't have tangents memorized, but I know that this is the same thing as the sine of 5 pi over 6 divided by the cosine of 5 pi over 6. And because there's a 6 in the denominator of the radian value, I know it's going to be some multiple of 30 degrees because I know pi over 6 is 30 degrees. Now, instead of trying to memorize these, I don't want you to do that. I want you to go and draw a unit circle. This is exactly how I do it, right? And so I need to figure out where 5 pi over 6 is. If this is a 30-degree angle, this is 1 pi over 6, then 2 pi over 6, then 3 pi over 6, then 4 pi over 6, 5 pi over 6. So 5 pi over 6 is over here, right? And it's literally 30 degrees away from the x-axis over here, 30 degrees, right? Whereas 1 pi over 6 is here, 30 degrees away, 5 pi over 6 is 30 degrees away over here. Because in my mind, I always think if it's a multiple of 30 degrees, I know what the sine and the cosine are. And so that's why I do it that way. So what's the sine of 5 pi over 6? Well, what's the projection over here? It's a positive projection on the y-axis. And sine of 30 is 1/2, and so I know it's got to be a positive 1/2 in the numerator. All right? In the denominator, the cosine of this is cosine of essentially of 30 degrees. Cosine of 30 degrees normally is square root of 3 over 2, but since it's over here, it's going to project to the negative axis to be negative square root of 3 over 2. And so all I have to do is simplify this. This is a fraction divided by a fraction, so 1/2. I'm going to multiply. I'm going to flip over here. It's going to be negative 2 over root 3. The 2's will then cancel. And so what you're going to have is negative 1 over root 3. Now, this is fine, I guess. You could leave it like that, but usually we don't like to do that. Negative 1 over root 3. What you want to do is you want to multiply you don't want a radical in the bottom. So you want to multiply top and bottom by square root of 3. Okay? And then what you're going to get, it's still a negative value. On the top, you're going to get a square root of 3, and on the bottom, you're going to have a square root of 9, which just gives you back a 3, and you get rid of the radical. So it's negative square root of 3 over 3, checking my answer. Yep, negative square root of 3 divided by 3. All right, but notice the actual basic part of learning the identity was just to identify it and to do this, but then you had to go and do some fraction arithmetic, which I made a mistake on. It happens all the time. I didn't want to erase it. I want to show you I make mistakes too, so that you don't get discouraged when you make your own mistakes. But anyway, we recovered from that, figured out that the angle was a nice one that we could figure out the tangent of, but then you had to remember the tangent was sine over cosine. Then you had to go to the unit circle and figure out what the tangent was, and then you had to do the algebraic manipulation to get to the correct answer. So there's multiple little steps in a problem that looks very simple. And often the difficulty is in those little steps, not in the big picture. All right, next what we want to do, I think we only have 2 problems left. We'll see if we can fit them on one board. Maybe we won't. I want to calculate what the tangent of 75 degrees is, not using a calculator. Now, there are many ways to do it. In fact, on my paper, I have 2 ways, because the first way I did it was long. I got the correct answer, but I was like, man, this is so many steps. And so I went a different way, totally different way, and it's a much simpler path, but you get to the same place. So I was just pointing that out to you because I don't know what the shortest path is when I start this. Nobody does. How do you find the tangent of 75? That's not an angle that's easy to remember or that we have memorized from trig. But what I do recognize is that I can rewrite this. Because I have double angle and half angle, right? I can write this as 150 degrees divided by 2. Now, why would I want to do that? Because when I go to the tangent identities for half angle, I have 3 of them to choose from. But notice that in all of them, if I have some angle divided by 2, whatever's in the numerator, this theta, I'm just taking the cosine or the sine of it over here. Now, I don't know what the cosine or the sine of 75 degrees is. That was the whole problem. But by writing it like this, what I'm going to end up doing is taking the cosine or the sine of what's in the numerator, which is 150 degrees. 150 degrees is only 30 degrees away from the x-axis, 180 degrees. So I know what the sines and the cosines of 150 degrees is. That's why I'm going to choose to write this as a half angle identity. Now, there are many other ways that you could go to get this answer. And you know, that's fine. There's always more than one way. But that's the thought process. Now, which of these am I going to pick? I'm going to tell you right now, I'm going to steer clear of the first one unless I have to. In fact, my first path through this problem, I actually use the first identity. The problem is that you have a complex numerator and denominator, and you have a radical there, and it makes it difficult to deal with. It's fine. It's all doable. It's just you have to deal with the radicals. It's just not fun. I get to the correct answer, but it's a lot of little steps to make sure that you can get there. So instead of doing that, do yourself a favor and use one of the other ones. These are just much simpler. I'm going to rewrite this one, and we're going to go with this one. You could easily use this one, no problem, but I'm going to use this one right here. So tangent theta over 2. So what we're going to do is we're going to go over here, and we're going to write the identity that we're going to use. Did I write it down on my paper here? Yes. So what I'm going to say is the tangent of theta over 2 is equal to the sine of theta, whatever's in that numerator, and then 1 plus the cosine of whatever's in that numerator. Let me double check myself. Sine of theta, 1 plus cosine of theta for tangent theta over 2. So again, the issue was I don't know what the tangent of 75 degrees is, but if I write it like this, then I'm going to end up taking sines and cosines of this 150 degree angle, because it will be written as the sine of 150 degrees, whatever's in the numerator, divided by 1 plus the cosine of 150 degrees, like this. Okay, now, how do I figure out the sine and the cosine of these angles? Now, unless you're a human computer, you're not going to remember. All right, so what you do is you say, well, 150 degrees, if this is 180 over here, then right here is 150 degrees. And you know that the difference between them is 30 degrees. Just like you know the 30-degree angle over here, this is a 30-degree angle to the x-axis over here. So what I'll say is, what is the sine of this? The projection will be here. It's essentially the sine of 30 degrees projected in a positive axis there. It's going to be 1/2 in the numerator. And then you're going to have 1 plus the cosine of this. Normally, the cosine of 30 degrees is square root of 3 over 2. Right? Normally it's square root of 3 over 2. And, but because it's over here on the negative side, it's projecting to the negative x-axis. So it's actually negative square root of 3 over 2. So you have to be careful and that's why I draw the unit circle, because if you don't draw the unit circle, it's very easy to get the incorrect sign. So what you're going to have here is a 1/2 on the top. On the bottom, you're going to have 1 minus square root of 3 over 2. And now it becomes an algebra problem. Everything is essentially done as far as the trig goes. How do we simplify this? Well, what we're going to do, we're going to collect everything together with a common denominator in the bottom. 1/2. I'm going to rewrite this 1 as 2 over 2 only because I'm trying to get a common denominator with this, right? So again, I'm going to have 1/2 in the top, and now I can say 2 minus square root of 3. Just subtract those numerators over that single denominator. I have now a fraction division, so I'm going to change it into multiplication, flip and multiply. So it's going to be a 2 on the top and a 2 minus the square root of 3 on the bottom. Now the 2's cancel, and so what you're going to have is 1 divided by 2 minus square root of 3. Now this actually is the answer. When you go to a calculator, let me just double check myself here. Yeah, 1 over 2 minus square root of 3, yeah. If you take 75 degrees and take the tangent of it and see what the decimal is, and if you calculate this, take the square root of 3, 2 minus that number, 1 divided by whatever you got, you're going to get the same thing because it numerically is correct. But in math, we don't like radicals in the denominator of fractions. So I have to teach you and I have to push you to get rid of it. How do we get rid of it? We have to multiply by what we call the conjugate over here. So what we're going to do is we're going to say this is going to be 1 over 2 minus square root of 3. What we're going to do is multiply by 2 plus the square root of 3. You'll see why we change it to a plus in the second. All we're doing is multiplying by the number 1. This is the number 1, so it doesn't change anything, but it's going to eliminate the radical from the numerator. When we multiply by 1, you're going to get 2 plus the square root of 3. What are we going to have in the denominator? This is like FOIL right here, essentially. So you have to multiply the first term. This is a multiplied, right? So the first terms, 2 times 2 is 4. These terms multiplied is minus 2 times the square root of 3. These outer terms is a positive 2 times the square root of 3. And then over here, here's where you have to think. You have negative times positive, which means you're going to have a negative sign here. But then you have square root of 3 times square root of 3. That, when you multiply under the radical, will be square root of 9, but the square root of 9 is just the number 3. So the negative sign comes from the sign, and then radical times radical gives you square root of 9, which is 3. Now these actually cancel. So on the top, you're going to have 2 plus square root of 3 over 4 minus 3, which is just 1. So the whole thing is 2 plus square root of 3. Let me just double check myself. 2 plus the square root of 3. This is the final answer. All right, so again, if you take 75 degrees, hit the tangent in the calculator, get some decimal, and you calculate this, you will get exactly the same decimal value, which is the same as this. It's just that we don't like these radicals in the denominator of fractions, okay? As I said, getting it down to this point, this is really where the kind of the trig sort of stops, and then dealing with radicals and multiplying and knowing the rules of algebra, where the rest of it kind of ends up. All right, I think, let me double check myself. I think I will be able to hopefully squeeze the last problem in to our little last bit of board here. What if we want to calculate the tangent of 22.5 degrees? I don't know what the tangent of 22.5 degrees is, right? But I know that 2 times 22.5 is exactly 45 degrees, and 45 degrees is a magic angle. I always know the sines and the cosines and the tangents of any multiple of 45 degrees. So I'm going to choose to rewrite this. Instead of being the tangent of this angle, I'm going to write it as the tangent of 45 degrees over 2. Because this division is 22.5, so these are the same thing. But now I've written it as a half angle identity, right? Which is the exact same identity that we used in the previous lesson. Anytime you have tangent angle over 2, you can use any of these. But I always steer clear of using this if I can help it. We just used this one in the last lesson, in the last problem, and you could absolutely use it again. But just for variety, let's use this one, just to show you there's like no preference, right? So this is an easy one too. So it's going to be 1 minus cosine what's in the top divided by sine of what's on the bottom. Now I'm running out of board space, so I do have to make an executive decision. Even though I usually rewrite everything and all of that, I'm going to write it as follows. I'm just going to go ahead and put it into the identity. 1 minus cosine of whatever's in the numerator, 45 degrees, divided by the sine of whatever's in the numerator, 45 degrees, in the numerator there. 1 minus cosine divided by sine. 1 minus cosine divided by sine. 1 minus cosine divided by sine, whereas we're operating on what's in the numerator, which is 45 degrees. So it's 1 minus cosine divided by sine. So all we have to do is evaluate this. Now the nice thing about this is that on the top it's 1 minus cosine 45 degrees is easy to remember, square root of 2 over 2. On the bottom, sine of 45 degrees is square root of 2 over 2. Again, easy. But in order to simplify it, we have to first fix the numerator. I'm going to rewrite the 1 as 2 over 2, just so that I can have a common denominator with over here being a 2. And I got to write this over here. Whoops, if I can write square root of 2 over 2 correctly. And in the top, I have a common denominator, so it's going to be 2 minus the square root of 2 over 2, and that's all divided by square root of 2 over 2. All right, I just, in the numerator, subtract the numerators, keep the same denominator, and now I have a fraction, an ugly one, divided by another fraction. So what it's going to be is square root of 2 minus, I've already messed up. Sorry about that. It's going to be 2, got to get my palm out now. 2 minus the square root of 2 over 2. I'm going to change this division into multiplication and flip and multiply it. So it's going to be 2 over square root of 2. Cancel, cancel. All right? So what I'm going to have over here, I'll switch colors, is going to be, since there's just a 1 here now, to be 2 minus square root of 2 over square root of 2. Now this is the correct answer, but again, we don't like radicals in the denominator. So what we're going to do is we're going to rationalize it. 2 minus the square root of 2 over square root of 2. How do I get rid of the radical in the bottom? I'm going to multiply by square root of 2 over square root of 2. I'm multiplying by 1 here. So in the numerator, what am I going to, let me use purple actually. What am I going to get? I'm going to, remember, this is like invisible parentheses around this, so this gets multiplied times the 2. 2 times the square root of 2. The minus sign is here. And now you have square root of 2 times the square root of 2. So that's like the square root of 4. Square root of 4 is 2. So anytime you have two square roots multiplying with the same thing there, essentially what's on the inside comes out. Okay? And on the bottom you have the same thing, just a 2. Because you have the square root of 4 here, which is 2. Now, again, I got rid of it. I got rid of the radical, so I could leave it like this, but I'm going to choose to simplify it further. I'm going to divide each term by 2. So it'll be 2 root 2 over 2 minus 2 over 2. Now I have a cancellation in 2's, and so what I'm going to have is the square root of 2 minus 1, because that becomes a 1 right there. Square root of 2 minus 1, and that is the final answer. And I barely slid into home to fit that on the board. So I said that at the end of it, I would give you a few minutes of showing you where some of these identities come from. Now, you could stop here. It's fine, because to be honest with you, the tangent identities are just not as important as the other ones. We do use them, they do come up, but not as much as the other ones. That's why we have kind of put them off to the side and we deal with it ourselves. But I do want to show you that they don't come from nowhere. And so what I'm going to do is just kind of go over here, and I'm not going to do all of them. I'm going to just show you where a couple of them come from. All right, let's go with the easiest one first. We're trying to figure out what the tangent of 2 times alpha is. So what we're going to do is I'm going to write tangent of 2 alpha as a tangent of alpha plus alpha. If I'm trying to find tangent of 2 times an angle, it's the same thing as the tangent of the angle plus the angle. You would agree with that, right? And then I already have a previous identity, which I haven't proved to you, up here on the board. Any two angles added together, you could just use this thing, but the angles are the same, alpha and alpha. So this is the same thing as tangent of alpha plus tangent of alpha over 1 minus tangent of alpha tangent alpha. Make sure you understand, when the angles are the same, then everywhere you see a beta, you just put an alpha, and that's all I did. I substituted in here. So in the numerator, what you have is tangent plus tangent of the same angle is 2 times the tangent of the angle. And on the bottom, you have 1 minus tangent, because this is tangent squared of the same angle. And notice that's exactly what the identity is. So this identity literally comes from using one of the addition identities and simplifying it down. You don't even really need it, but we have them because they do pop up and they are useful. Okay? Again, we're not going to do all of them, but let's do, or let's talk about one of these other ones down here. All right, let's talk about the half angle identity. All right, let's look at the first one here. The half angle identity, tangent of the angle over 2. Anytime you have a tangent, it's sine over cosine, right? So this is the same as sine of theta over 2 over the cosine of theta over 2. Because anytime you have a tangent, it's just sine over cosine, right? But we already have identities for sine and cosine. On the previous board, we already know the sine of any half angle is this, and the cosine is this. And now you can see where the radicals are coming from. It's going to be this term divided by this term. And so it's going to be ugly, but I'm just going to write it down. What you're going to have, where do I write it? Where do I want to write it down? I guess I'll do it over here. So you're going to have in the numerator plus or minus, you're going to have 1 minus cosine of theta over 2. You're going to have a square root around that. All that's going to be divided by 1 plus cosine of theta over 2. You're going to have the radical there, and you're going to have the plus or minus right there. But what happens whenever you have a radical divided by a radical? Well, then the radical can extend over the whole entire fraction. And then you have all this stuff on the inside that you can simplify. So what's going to end up happening is you're going to essentially make the radical larger. I don't have room to put it all, but you're going to make the radical larger. It's going to be this divided by this. You're going to flip and multiply. The 2's are going to then essentially cancel. And when you flip and multiply on the inside, what you're going to have, the plus or minus will stay out there, and you're going to have 1 minus cosine of theta over 1 plus cosine of theta, and the radical will be right there. Let me just double check, which is exactly what we have right here. Now make sure you understand where that comes from. We'll just extend the whole radical around the whole fraction, then you have fraction divided by fraction, flip and multiply, the 2's cancel, and then it'll be this divided by this, and that's where it comes from. So you can see that these ugly looking identities are coming from other identities that we've already proven. Now, the one that I didn't prove yet is the one at the top, and that is because it's just a little bit more algebraic steps to get there. But I'm going to start it just so that we can talk about it a little bit. I'm not going to do the whole thing. Basically, what you can do is that you can say that the tangent of any two angles added together is sine over cosine, right? So you can call this the sine of alpha plus beta, and you can write this as the cosine of alpha plus beta. Because anytime you have the tangent, it's just a sine over cosine, right? But we already have identities for the sine of two angles added together and the cosine of two angles added together. The sine of two angles added together is this monstrosity, and the cosine of two angles together is this monstrosity. So if you replace what I have on the board with this line, and then replace this with this line, essentially you're going to have a large expression on the top and a large expression on the bottom. Now, that's where I'm going to leave it, because it's not super hard, but it's about 4 more lines that I don't have time to show you and a space on the board to show you. But if you do that substitution and manipulate it and factor out terms and cancel a couple of things, then you can put it into this form, right? Last thing I'll say is, how do you go from here to here? Well, you can do the same kind of thing, tangent of this over this, and we already know the tangent is sine over cosine. So sine of this divided by cosine of this, we know what those are. But we also know that we can just go straight from here to here, because if this is alpha plus beta, we can get this by just replacing beta with negative beta. In other words, use this one that we've already proven and replace the angle beta with the angle negative beta. Like, imagine replacing this with negative beta here and negative beta here. Now, tangent is an odd function. Tangent is an odd function, right? So we learned this before. The tangent of negative of an angle is negative tangent of the angle. The negative sign comes out, and it's because when you graph the tangent function, it's not symmetrical. It's what we call an odd function. So when we talked about even and oddness of sine and cosine and tangent, we said that whenever you have the tangent of a negative angle, it's equivalent to taking the tangent of the positive angle with a negative sign in front. So if you want to figure out what this is, just replace beta with negative beta. But because tangent of negative beta is the same as almost like pulling that negative sign out, then you pull the negative sign out there. Negative beta means you would pull a negative sign out there, changing it to a positive. So the reason these two look so similar is because replacing beta with negative beta essentially just flips the sign here and here, and that's what we have right there. So those are sort of abbreviated proofs, and certainly not for all of them. I did them mostly so you could say, okay, this is not black magic. I could get that. But I don't also want to spend 20 minutes going through every single one of them, because the tangent identities are just, in my experience, just not quite as important. Even though they are important, they're not as important. All right, so I'd like you to go down through this lesson, solve the problems yourself, follow me on to the last lesson where we're going to be conquering the tangent identities. Learn anything at mathandscience.com.